On a clear autumn night, far from city lights, you can see it with your bare eyes. A faint smudge of silver light, barely there, quiet and beautiful, sitting just above the horizon, like a soft brushstroke left behind by the universe. It looks like nothing. A small cloud, a trick of the atmosphere. Most people glance at it and feel calm. That smudge is the Andromeda galaxy, and it is one of the most terrifying things a human being can look at. Not because it is ugly, not because it is dangerous in any immediate sense, but because what it actually is, what it actually represents in terms of size, violence, and cosmic consequence, is so far beyond what that gentle smudge suggests that understanding it changes the way you think about where we live. If this is the kind of science that pulls you deeper into the real universe, take a second to like and subscribe. We do not chase clickbait here. We chase what is actually out there. Are you comfortable? Now, let's begin. On a clear night in autumn, if you are far enough from the nearest city, you can do something that almost no one alive today has done. You can look northeast, past the great square of Pegasus, into the constellation that carries the name of a princess from Greek mythology, and you can see another galaxy with your own eyes. No telescope, no binoculars, no app on your phone pointing the way, just your retina collecting photons that left their source 2.5 million years ago. It does not look like much. A faint oval smear, slightly brighter in the center, softer than a cloud, almost indistinguishable from a trick of the atmosphere. If you did not know what you were looking at, you would ignore it entirely. Most people do. On any given clear night, billions of human beings are technically within eyeshot of this object, and almost none of them notice it. The ones who do usually describe it the same way: pretty, peaceful, a quiet little glow. That glow is the Andromeda galaxy. And what you just experienced by looking at it is one of the most profound acts of deception the universe has ever performed on a human nervous system. Because the object your brain just filed under small, faint, and harmless is not small. It is not faint. And what it represents is so far removed from harmless that if you genuinely understood it, the calm you felt looking at that smudge would never come back the same way again. This is a story about how the most beautiful object in the night sky became the most misleading one, and about what happens when you peel the beauty back and look at what is actually sitting 2.5 million light-years from where you sleep. Before we get into what Andromeda actually is, we need to understand what it has been to us. Because humans have been staring at that same faint glow for a very long time and getting it wrong at almost every stage, the first known record of someone looking at Andromeda and writing down what they saw comes from the year 964. A Persian astronomer named Abd al-Rahman al-Sufi was compiling a catalogue of the stars, carefully updating the ancient Greek observations with his own meticulous work. He noted a small cloud in the constellation of Andromeda, a nebulous smear. He did not know what it was. He could not have known. He simply recorded it as something slightly unusual in the sky and moved on. For the next several centuries, that is where the story stayed: a smear, a cloud, an oddity. European astronomers eventually observed it through early telescopes and classified it as a nebula, a cloud of gas within our own galaxy. That classification felt comfortable. It kept the universe small and manageable. Everything visible in the sky was part of one system, the Milky Way, and the Milky Way was the universe. End of story. That comfortable idea held for centuries. It survived telescope improvements. It survived the discovery of other fuzzy patches scattered across the sky. It survived because it aligned with something deep in the human need for orientation. We are here, Everything is contained. The boundaries are known. By the early 20th century, the question had grown sharper, but no less contentious. Telescopes had improved dramatically. Hundreds of spiral nebulae had been catalogued across the sky, faint pinwheels of light that defied easy classification. Some astronomers insisted they were gas clouds within the Milky Way, swirling pockets of luminous material that would eventually be explained by local physics. Others suspected they were something far more radical. Separate galaxies, independent systems of stars, unimaginably distant, each one a universe unto itself. The argument was not merely technical, it was existential. If the spiral nebulae were local, the Milky Way remained everything. If they were distant, the known universe was suddenly a single building in a city of billions, and humanity's sense of cosmic centrality was an illusion. In April of 1920, the tension broke into the open. The National Academy of Sciences in Washington hosted what became known as the Great Debate, a public scientific argument between two astronomers with fundamentally opposing views of the cosmos. On one side stood Harlow Shapley, a brilliant and confident researcher who had recently made important contributions to measuring the size of the Milky Way. Shapley argued that the galaxy was enormous, far larger than previously estimated, and that the spiral nebulae were relatively small structures contained within it. The universe, in his view, was the Milky Way. One galaxy, one system, nothing outside it that mattered. On the other side stood Heber Curtis, an astronomer who had been studying the spiral nebulae for years and had assembled a body of evidence suggesting they were external galaxies at great distances. Curtis pointed to observations of novae, exploding stars detected in the Andromeda Nebula that appeared far dimmer than novae observed in the Milky Way. If they were the same type of event, the dimness implied an astonishing distance. He also noted that the spiral nebulae showed redshifts and blueshifts that were difficult to explain if they were merely local gas clouds. The debate ended without a clear winner. Both men presented compelling arguments. Both had weaknesses in their data. The scientific community remained split, and for the next 4 years, the question of whether the universe was one galaxy or many remained genuinely unresolved. It is worth pausing on that fact, because it reveals something important about the psychology of this story. The evidence that the Milky Way might not be everything was already accumulating. The observations were already pointing outward, but the idea that the universe was small and contained was so deeply satisfying, so aligned with the human need for manageable boundaries, that professional scientists with access to the best instruments on Earth could look at the data and still argue that the spiral nebulae were nothing special. The resistance was not ignorance. It was comfort, dressed in technical language. Then came the year 1924, and a man with a large telescope and an extraordinary eye destroyed that comfort permanently. Edwin Hubble was working at the Mount Wilson Observatory in California using the Hooker telescope, which at the time was the most powerful astronomical instrument on Earth, with its 100-inch mirror. He was studying the Andromeda Nebula, attempting to resolve its structure in greater detail. What he found were individual stars, not just any stars, a specific type called Cepheid variables. These stars pulse in brightness at a rate that is directly related to their intrinsic luminosity. If you know how bright something truly is, and you can measure how bright it appears, you can calculate how far away it is. The math is clean. The method was proven. Hubble did the math. And the number that came back was absurd. The Andromeda Nebula was not inside the Milky Way. It was not a gas cloud drifting among familiar stars. It was roughly 900,000 light-years away by his initial estimate, later refined to approximately 2.5 million light-years. It was not part of our galaxy at all. It was an entirely separate galaxy, a vast island of stars, dust, gas, and structure, sitting in its own region of space, separated from us by a void so enormous that light itself needed more than 2 million years to cross it. The implications hit the scientific community like a shockwave. In a single set of observations, the known universe expanded by a factor that the human mind was not built to process. Before Hubble, the Milky Way was everything. After Hubble, the Milky Way was one galaxy among what would eventually be revealed as hundreds of billions. The sky was not a ceiling. It was not a dome enclosing one system. It was a window into a depth so staggering that no analogy written in any language has ever fully captured it. The great debate was over. Curtis had been right in principle, even if some of his specific numbers had been off. Shapley had been wrong in conclusion, even though his work on the Milky Way's size was important. And the comfortable sky that both men had been arguing about had been shattered by a set of pulsating stars in a nebula that turned out to be a galaxy. And Andromeda was the object that broke the wall. That should have been the moment when humanity began to take Andromeda seriously. When the faint smudge stopped being a curiosity and started being understood as something enormous, something real, something that demanded respect and possibly fear. But that is not what happened. What happened instead was something quieter and, in its own way, more dangerous than ignorance. Andromeda became a poster. If you have ever walked through a gift shop at a science museum, scrolled through a space photography account, or seen a documentary about the cosmos that lingers on pretty visuals, you have seen the version of Andromeda that replaced the old nebula myth with a new one. It is the long exposure photograph, the one taken through high-powered telescopes with tracking mounts that follow the sky for hours, collecting light photon by photon, stacking image after image until what emerges is a spiral galaxy of breathtaking beauty, sweeping arms of blue and white stars, reddish clouds of hydrogen gas, dark lanes of dust threading between the arms like rivers. A bright golden core glowing with the concentrated light of billions of ancient stars. And all of it tilted at a gentle angle against a backdrop of perfect blackness dotted with pinpoint stars. It is, by almost any standard, one of the most beautiful images in all of science. And it is a lie. Not because the photograph is fake, the data behind it is real. Every photon in that image made a genuine journey across 2.5 million light-years of intergalactic space and arrived at a detector that faithfully recorded it. The lie is not in the data. The lie is in what the image makes you feel. When you look at that photograph, your brain does exactly what it was evolved to do. It takes a flat, bounded image and assigns it a scale that fits within your experience. The galaxy looks like it might be the size of a dinner plate, maybe a bicycle wheel. It is a contained, elegant shape with clear edges. It sits neatly within the frame. You can see all of it at once, which means your brain unconsciously categorizes it alongside other things you can see all of at once. A painting, a flower, a decorative object on a shelf. Your emotional response follows the visual cue. You feel appreciation, calm, a mild sense of wonder, and then you move on. Because the image told your nervous system that this object is manageable, nothing about that response is accurate. The photograph compresses a structure more than 200,000 light-years across into a few inches on your screen. It flattens three-dimensional depth into 2 dimensions. It freezes motion that unfolds across hundreds of millions of years into a single still frame. And it places the entire object within a border, which is perhaps the most deceptive part of all, because borders imply containment, and nothing about Andromeda is contained. Here is the part that almost never gets communicated in those pretty images. If you could somehow see Andromeda as it truly appears in the sky, not through a telescope, not in a photograph, but with your bare eyes enhanced to detect its full extent, you would not see a small smudge. The galaxy's visible disk spans roughly 3 degrees across your field of view. That is more than 6 times the apparent diameter of the full moon. Hold your hand at arm's length and extend your little finger. The width of that finger covers roughly 1 degree of sky. Andromeda's disk spans 3 of those finger widths. Its spiral arms would stretch across a patch of sky wide enough that you could not cover it with a single outstretched thumb, reaching into the surrounding darkness on both sides. The faint outer disk would extend further still, fading gradually into the background, but never quite disappearing, bleeding into the star field of the constellation itself. If your eyes could gather enough light to see it all, the galaxy would not be a smudge, it would be an apparition. A vast, tilted oval of silver and blue, draped across the constellation of Andromeda like a curtain of structured light, its spiral arms curving visibly across a patch of sky wide enough to contain dozens of the constellations you grew up learning. The bright central bulge would glow like a second moon, and the arms would trail away from it on both sides in great sweeping arcs, each one wider than the apparent distance between most stars you can see overhead. You would not need to search for it. You could not avoid it. It would be one of the most dominant features of the night sky, a river of ancient light so large that you would have to turn your head to take in both edges. But you cannot see it. Your retina is not sensitive enough. The photons from the outer arms arrive too few and too far between for the cells at the back of your eye to register. What you see instead is the bright core and nothing else, a keyhole, a tiny fraction of the actual structure presented to your brain without context, without scale, without any indication that the real object extends far beyond what is visible. Every time you have looked at that faint smudge in the autumn sky, you were staring through the body of another galaxy. The spiral arms were there. The outer disk was there. The structure that covers 6 moon widths of sky was there. And your brain, receiving only the brightest fragment, filed the whole thing under small and harmless and moved on. This is the first layer of the deception, and it sets the stage for everything that follows. Because once you understand that the image is misleading, you have to ask what it is actually hiding. And the answer to that question is what turns Andromeda from a beautiful object into something that should make you deeply uncomfortable. Start with distance, 2.5 million light-years. People hear that number and nod, the way you nod when someone tells you the national debt is $30 trillion. The number is too large to feel, so it becomes background noise. But distance in astronomy is not an abstraction. It is a physical gap, and crossing it, even in thought, requires confronting something that the human brain genuinely cannot do without help. Light is the fastest thing in the universe. Nothing with mass has ever been measured traveling faster. It crosses roughly 186,000 miles in a single second. In 1 year, it covers approximately 6 trillion miles. That distance, 6 trillion miles, is 1 light year. Now multiply that by 2.5 million. The space between you and Andromeda is approximately 15 quintillion miles. That is a 1 followed by 19 digits. If you drove a car at highway speed without stopping, the trip would take more than 28 trillion years. The universe itself is only about 13.8 billion years old. You would need to run the entire history of the cosmos more than 2,000 times to make the drive. And yet, Andromeda is close. That is the fact that begins to twist the comfortable picture into something else entirely. By galactic standards, 2.5 million light-years is a next-door neighbor. The observable universe is roughly 93 billion light-years across. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away. Andromeda sits so close to us that we share a gravitational system. We are bound to it, not poetically, not metaphorically, physically, gravitationally, measurably bound. The Milky Way and Andromeda are the two largest members of a collection called the Local Group, a cluster of more than 80 galaxies held together by mutual gravitational attraction. And within that group, the two of us dominate everything. Every smaller galaxy in the Local Group orbits one of us, or sits trapped somewhere in the gravitational landscape between us. You did not know that, probably. Most people do not. Most people think of galaxies as scattered randomly across space, each one floating independently like leaves on a pond. They are not. Galaxies cluster, they interact. They pull on each other across millions of light years. And the two biggest gravitational players in our immediate cosmic neighborhood are us and Andromeda. We are not observing Andromeda from a safe distance. We are locked into a system with it. That locked system has a history, and the history is not calm. The light you see when you look at Andromeda left the galaxy approximately 2.5 million years ago. On Earth at that moment, the genus Homo was only just emerging. Stone tools were new. Fire was still a long way off. The light predates every civilization, every written word, every human thought about the sky that would eventually receive it. That fact alone should reframe how you feel about the smudge. You are not looking at a galaxy as it is now. You are looking at a portrait from the deep past, a message sent before the audience existed. But the delay also means something else. It means the Andromeda you are looking at and the Andromeda that exists right now are not in the same place. Over 2.5 million years, Andromeda has moved. It has rotated. Its stars have been born and died by the billions. Its structure has shifted, and critically, it has traveled closer to us. At its measured approach, speed of approximately 110 kilometers per second, Andromeda has closed the gap by a meaningful amount in the time that light took to reach your eyes. You are looking at a galaxy that is no longer where it appears to be and is closer than the image suggests. The sky is showing you a memory. And the memory is already outdated. This disconnect between appearance and reality runs through every aspect of how Andromeda presents itself to the human eye and mind. Consider how it sits in popular understanding. If you ask an average person what Andromeda is, the ones who know anything about it will usually say one of two things. It is the nearest galaxy to us, or it is the galaxy that is going to collide with the Milky Way. Both of those statements are approximately true, but profoundly incomplete. And the incompleteness is where the real story hides. Saying Andromeda is the nearest galaxy suggests that it is simply the first item on a long list of similar objects. It frames Andromeda as a data point, the closest of many. But what that framing hides is the relationship. Andromeda is not just close in a spatial sense, it is close in a structural sense. It occupies the same gravitational territory as the Milky Way. The two galaxies share satellite companions. Their dark matter halos, the vast invisible structures of exotic matter that surround every major galaxy, may already be overlapping. Hubble Space Telescope observations have measured Andromeda's gaseous halo extending nearly 1 million light-years outward from the galaxy's visible disk, 1 million light-years. That is roughly half the distance between the two galaxies. The halo of Andromeda reaches toward us across the intergalactic void like an invisible arm, and our own galaxy's halo reaches back. The two systems are not separated by clean, empty space. They are bleeding into each other at the boundary. When you looked at that faint smudge in the sky and felt calm, you were standing inside the influence zone of what you were looking at. And saying that Andromeda will collide with the Milky Way, while dramatic, reduces a complex gravitational relationship to a single future event. It turns an ongoing interaction into a headline. It makes people think of a crash, a bang, a defined moment of impact. None of that is how galactic interactions work. The relationship between Andromeda and the Milky Way is not a single event in the future. It is a process that is happening now, has been happening for billions of years, and will continue for billions more, regardless of whether the galaxies eventually merge or not. Gravity does not wait for a collision to exert its influence. It is always there. Right now, at this moment, Andromeda's mass is pulling on the Milky Way, and the Milky Way's mass is pulling on Andromeda, and that mutual pull is shaping the trajectory of both systems through space. You cannot see that. You cannot feel it. There is no human sense that registers the gravitational influence of a galaxy 2.5 million light-years away. But it is as real as the ground beneath your feet. More real, in some ways, because the ground is a temporary surface on a temporary planet, and the gravitational relationship between these two galaxies has been operating since before either one fully formed. This is the lie that the beautiful image tells. Not a lie of fabrication, a lie of omission. The image shows you the light and hides the gravity. It shows you the shape and hides the scale. It shows you a still frame and hides the motion. It shows you a bordered photograph and hides the fact that what you are looking at has no border, no edge, no boundary that your intuition can wrap itself around. And it hides something else. Something that requires going deeper than the visual, deeper than the distance, deeper than the gravitational arithmetic. It hides what Andromeda actually is when you stop treating it as an image and start treating it as a physical object. Because the faint smudge in the sky is not a picture of a galaxy. It is the visible fraction of a structure so vast, so dense, so violently assembled, and so consequential to the future of everything around it that calling it beautiful is like calling a hurricane photogenic. It might be true, but it misses the point entirely, and the point begins with a number: 1 trillion. That is how many stars Andromeda contains, not millions, not billions. 1 trillion individual nuclear furnaces, each one a sphere of superheated plasma held together by its own gravity, each one burning through millions of tons of hydrogen every second, each one separated from its nearest neighbor by distances so large that even within the galaxy, the emptiness between stars dwarfs the stars themselves. 1 trillion of them, arranged in a disk more than 200,000 light-years across, orbiting a center that holds something far more violent than starlight. The smudge does not show you any of that. The photograph does not communicate any of that in a way your nervous system can absorb. 1 trillion is a number you can hear but cannot feel. And the gap between hearing it and feeling it is exactly the gap this story is trying to close. The beautiful image told you Andromeda was a decoration, something to admire, something to put on a poster and hang on a wall. What it actually is has nothing to do with decoration. What it actually is requires a different kind of seeing, and that is what comes next. Because now that the image has been named for what it is, a compression, a flattening, a visual sedative that makes a colossal neighboring galaxy feel like a harmless ornament, we can start to unpack what the real Andromeda looks like when you strip the beauty away and measure what remains. What remains is not calm. What remains is not small. And what remains is closer to you than you were ever comfortable knowing. Let us begin with the disk. The visible body of Andromeda, the part that shows up in photographs, stretches approximately 220,000 light-years from one edge to the other. That number deserves more than a glance, because it is the foundation on which everything that follows rests, and the human brain will try to slide past it the way it slides past any number too large to picture. So, slow down. 220,000 light-years. A single light-year is roughly 6 trillion miles. Multiply that by 220,000, and you arrive at a diameter so large that no metaphor borrowed from daily life can honestly represent it. The entire orbit of Neptune around our Sun, the widest loop any major planet traces in our system, could be dropped into the disk of Andromeda and it would vanish. Not shrink, vanish. The solar system would be so small relative to the galaxy that it would occupy less space than a single grain of sand sitting in the center of a football field occupies relative to the stadium around it. And that comparison still understates the difference by orders of magnitude. The solar system is roughly 1 light day across if you measure generously out to the edge of the Oort cloud. Andromeda's disk is more than 80 million light days wide. Your entire cosmic address, every planet, every moon, every asteroid, every frozen body at the ragged fringe of the sun's influence would be an invisible speck inside it. That is the structure you saw as a smudge. Inside that disk, the numbers escalate beyond easy comprehension. Andromeda contains approximately 1 trillion stars. Current estimates place the Milky Way's star count somewhere between 200 billion and 400 billion. Andromeda holds roughly 3 to 5 times more. 1 trillion is a number people encounter in economic contexts and rarely anywhere else. And even in economics, it tends to produce a glazed stare rather than genuine understanding. In this context, it means something very specific. It means that if you could count 1 star per second without stopping, without sleeping, without pausing for a single breath, the count would take approximately 31,700 years. You would begin counting during the last ice age and still not be finished today. Each of those trillion stars is a thermonuclear engine. Each one is converting millions of tons of hydrogen into helium every second through fusion reactions in its core. Each one is producing energy that radiates outward in every direction at the speed of light. Some of them are small red dwarfs, dim and long-lived, burning their fuel so slowly they will last trillions of years. Some are blue supergiants, bloated and unstable, pouring out energy at rates that will exhaust them in a few million years before they explode in supernovae that briefly outshine the entire galaxy. Some are pulsars, spinning remnants of dead stars, sending beams of radiation sweeping through space like cosmic lighthouses. Some are binary systems, pairs of stars locked in mutual orbit, exchanging mass, distorting each other's shapes, occasionally triggering thermonuclear detonations on their surfaces that flare across thousands of light years. 1 trillion of these objects, packed into a spinning disk. And that disk is not a flat, uniform structure the way a photograph suggests. It has depth. The disk is roughly 1,000 light-years thick in the outer regions and thickens considerably toward the center, where a bulge of older, redder stars swells outward, above and below the plane. The spiral arms, those iconic sweeping curves, are not solid features. They are density waves, regions where stars, gas, and dust crowd together more tightly, triggering waves of star formation as material passes through. The arms are constantly forming and dissolving on timescales of hundreds of millions of years. The galaxy you see in a photograph is not the same galaxy that existed when that light began its journey. The structure itself is alive in a way that a still image can never communicate. Now move to the center, because at the very heart of this 1 trillion star structure, hidden behind thick lanes of dust and gas, something sits that makes the surrounding stars look gentle by comparison. Andromeda's central supermassive black hole carries an estimated mass of 100 million to 140 million times the mass of our Sun. That range of uncertainty itself reveals how difficult this object is to study, but even the low end of the estimate is staggering. The Milky Way's own supermassive black hole, Sagittarius A star, weighs roughly 4 million solar masses. It is a monster by any earthly standard. Andromeda's black hole outweighs it by a factor of 25 to 35. It is not just larger, it is categorically more massive, sitting in a different class of gravitational object entirely. The black hole itself is not large in spatial terms. Its event horizon, the boundary beyond which nothing escapes, spans a region smaller than our solar system. But the mass, compressed within that boundary, warps space-time so severely that light passing near it bends, clocks near it slow, and matter falling toward it is accelerated to velocities approaching the speed of light before being superheated into a plasma that radiates across the electromagnetic spectrum. Observations from NASA's Chandra X-ray Observatory have tracked the black hole's X-ray emissions over 15 years and found significant variability. In 2013, a dramatic flare was recorded, a sudden spike in high-energy radiation suggesting that a significant quantity of material had crossed the threshold and been consumed. That flare was not an explosion in the conventional sense. It was the sound, translated into radiation, of matter being destroyed at the most fundamental level available to physics. Andromeda's nucleus is unusual in another way. Hubble Space Telescope observations revealed that the center of the galaxy contains not one, but two distinct concentrations of light, designated P1 and P2, separated by roughly 5 light-years. Most galaxies have a single bright center. Andromeda has two, and the relationship between them is one of the strangest structural features ever observed in a galactic core. P2 marks the true gravitational center, the location of the supermassive black hole. P1 is a dense concentration of stars offset from that center, and its position puzzled astronomers for years after its discovery. The explanation that eventually emerged is rooted in orbital mechanics operating under extreme gravitational conditions. P, or, is not a separate structure sitting beside the black hole. It is part of an eccentric disk of stars orbiting the black hole on elongated paths. Those stars swing close to the black hole on one side of their orbit, where they are accelerated to enormous velocities by its gravitational pull, whipping around the center at speeds that make them nearly impossible to resolve individually. Then they arc outward to the far end of their orbit, where they slow down. Stars on elliptical orbits spend more time at the distant, slow-moving end than at the close, fast-moving end. The result is that the stars pile up visually at the far point of their orbit, creating the appearance of a bright concentration offset from the true center. P1 is not a place where stars live. It is a place where stars linger, a gravitational illusion created by the orbital dynamics of a stellar population trapped around 100 million solar mass black hole. Nothing like this exists in the Milky Way. Our galaxy's central black hole is surrounded by a comparatively orderly stellar environment. Andromeda's core is a dynamic system where stars trace extreme orbits at velocities that would shred any structure less tightly bound, where the asymmetry of the double nucleus has persisted for hundreds of millions of years as a stable but violent equilibrium, and where the very geometry of the light that reaches our telescopes is shaped by the warping influence of the black hole's gravity. And here is what matters for this story. In photographs, Andromeda's core looks like the calmest part of the galaxy. A smooth, bright, golden bulge, featureless and warm. It is the visual anchor of the image, the part your eye rests on, the part that feels most stable and most settled. In reality, it is the most dynamically extreme region in the entire system, a place where stars orbit a gravitational engine at velocities that would be lethal to any less tightly bound structure. A place where the remnants of a consumed galaxy's stellar population trace an eccentric path that has been sustained for longer than complex life has existed on Earth. A place where the double nucleus itself is a frozen record of gravitational violence that the photograph flattens into a featureless glow. The core of Andromeda is not calm. It is a crime scene that looks calm because the evidence is moving too slowly and too far away for human senses to read. The very center of the galaxy, the region that appears most peaceful in every image you have ever seen of it, is in fact the most vivid proof that appearances and reality diverge at every level of this object. That scar at the center is not the only one. In 2018, a study published in Nature Astronomy by Richard D'Souza and Eric Bell at the University of Michigan pieced together evidence that Andromeda underwent one of the most violent events in the recent history of the local group. Approximately 2 billion years ago, a massive galaxy, the third largest member of the local group at the time, fell into Andromeda and was torn apart. This galaxy, which the researchers named M32P, carried a stellar mass of roughly 25 billion times that of our Sun. It was not a small satellite being nibbled at the edges. It was a major galaxy in its own right, and Andromeda destroyed it. The destruction was not instantaneous. It unfolded over hundreds of millions of years in a process of extraordinary gravitational violence. As M32P fell inward toward Andromeda, the tidal forces between the two systems began to stretch and distort the smaller galaxy's structure. Stars in its outer regions were the first to be stripped away, peeled off layer by layer as differential gravity pulled harder on the near side of the galaxy than on the far side. Those stripped stars did not vanish. They were flung outward into enormous arcing streams that wrapped around Andromeda's halo, tracing the orbital path of their destroyed parent like debris scattered along a highway after a wreck. As the smaller galaxy spiraled deeper into Andromeda's gravitational well, the stripping intensified. The disk of M32P was torn apart. Its gas was compressed and heated by the interaction, triggering furious bursts of new star formation even as the galaxy that contained them was being shredded. Entire stellar populations were born inside a system that was dying, created by the very forces that were dismantling their home. The compressed gas clouds collapsed and ignited in waves, lighting up the merger zone with the ultraviolet glow of hot young stars, forming at rates far exceeding anything in Andromeda's normal history. At the center of M32P, a dense core of stars resisted the tidal forces longer than the surrounding structure. While the outer layers were ripped away and scattered across hundreds of thousands of light-years of Andromeda's halo, the core remained gravitationally bound, compact enough and dense enough to survive as a coherent object even as everything around it was consumed. That surviving core is what we see today as the satellite galaxy M32. It orbits Andromeda as one of its closest companions, a small, dense, peculiar galaxy that has puzzled astronomers for decades because it does not look like anything else in the local group. It is too compact, too bright for its size, and its stellar population contains intermediate-age stars that should not be there in a typical dwarf elliptical galaxy. Those stars are the remnants of the final burst of formation that occurred as M32P was being destroyed. M32 is not just a satellite galaxy, it is a corpse. The stripped, compressed, gravitationally truncated remnant of what was once the third largest galaxy in the neighborhood. The evidence for this is written across Andromeda's body. The galaxy's stellar halo, the diffuse cloud of stars surrounding the main disk, is unusually large and unusually rich in metals, a chemical signature that points to a massive disrupted companion. The giant stellar stream, a vast river of stars arcing through Andromeda's halo, is likely debris thrown outward during the merger. The merger triggered a global burst of star formation across Andromeda roughly 2 billion years ago, during which an estimated 1/5 of the galaxy's current stars were born. The disk thickened. The halo expanded. The structure of Andromeda, as it exists today, is, in significant part, a consequence of this single act of destruction, and it was not the only one. Studies of Andromeda's globular clusters, the ancient dense balls of stars that orbit within and around the galaxy, have revealed two distinct populations based on their orbital properties. One population orbits in a way consistent with having formed within Andromeda itself. The other follows orbits that suggest they were captured from galaxies that Andromeda consumed at different times in its history. The data points to at least two major accretion events, one recent and one far older, potentially 10 to 12 billion years ago, during the earliest chapters of the galaxy's existence. Andromeda has been eating its neighbors for most of its life. The galaxy you saw as a smudge of light has a body count. Now go beyond the visible. Because the disk, the trillion stars, the black hole, the spiral arms, the stellar halo littered with the remains of consumed galaxies, all of that is only a fraction of what Andromeda actually is. The majority of the galaxy is invisible. Observations of Andromeda's rotation curve, the way stars orbit at various distances from the center, provided some of the earliest and most compelling evidence for the existence of dark matter. In the 1960s and 70s, astronomer Vera Rubin and her colleagues measured how fast stars in Andromeda's outer disk were moving. If the galaxy's mass were concentrated in its visible stars and gas, as conventional physics predicted, those outer stars should have been orbiting slowly. The further out you go from the center of a galaxy, the less visible mass there is pulling inward, and the slower the orbital speed should be. This is how gravity works in any system where you can see all the mass. It is how the planets in our solar system behave. Mercury, closest to the Sun, orbits fastest. Neptune, farthest out, orbits slowest. The prediction for galaxy rotation was the same. Stars at the edges should crawl. They were not crawling, they were racing. Rubin's measurements showed that stars in Andromeda's outer disk were orbiting at velocities nearly as high as stars much closer to the center. The rotation curve, instead of declining as expected, stayed flat. It extended outward, far beyond the visible edge of the galaxy, at speeds that the gravitational pull of all the stars, gas and dust combined, could not explain. Something else was there. Something massive. Something that extended far beyond the visible disk and exerted gravitational force on everything within reach, but that emitted no light, reflected no light, and interacted with no instrument designed to detect electromagnetic radiation. That something is dark matter, and in Andromeda it dominates everything. Current estimates suggest that approximately 90% of the galaxy's total mass is dark matter. The visible galaxy, every star, every cloud of gas, every grain of interstellar dust accounts for roughly 10% of the gravitational budget. The remaining 90% is a vast halo of exotic matter that does not emit light, does not absorb light, does not interact with the electromagnetic spectrum at all, and is detectable only through its gravitational influence on the matter we can see. Let that settle for a moment. When you look at Andromeda, either with your eyes or through the most powerful telescope on Earth, you are seeing less than 10% of the galaxy. The other 90% is there. It is real. It is exerting gravitational force on every visible object in the system. It is shaping the orbits of 1 trillion stars, and it is completely invisible. The photograph of Andromeda that hangs on the wall at the Science Museum, the one that looks so complete, so elegantly framed, is a portrait of a fraction. It is as if you photographed the visible tip of an iceberg and labeled it the whole structure, except the ratio is worse. An iceberg shows roughly 10% of itself above water. Andromeda shows roughly 10% of itself in light. The proportions are similar, but the scale is incomprehensibly larger. The hidden mass of Andromeda is not a few thousand tons of ice beneath the waterline, It is hundreds of billions of solar masses of matter that no human sense and no conventional instrument can directly detect. Andromeda's dark matter halo is estimated to extend far beyond the visible disk. Depending on the model, the halo's outer boundary may reach 600,000 light-years or more from the galaxy's center, creating a gravitational sphere of influence that dwarfs the already enormous stellar disk. The visible galaxy, the part that shows up in photographs, is sitting inside a much larger, invisible structure, the way a pit sits inside a fruit. And it is the invisible part that holds everything together. Now, layer on the gaseous halo. In 2015, a team led by Nicholas Lehner at the University of Notre Dame used the Hubble Space Telescope to study the circumgalactic medium of Andromeda, the vast atmosphere of gas that envelops the galaxy far beyond its stellar disk. The technique was indirect but elegant. The team observed 18 distant quasars, intensely luminous objects billions of light-years behind Andromeda, and analyzed how their light was absorbed as it passed through the galaxy's surrounding gas. Different elements absorb light at specific wavelengths, leaving fingerprints in the spectrum that reveal the composition, temperature, and extent of the gas the light traveled through. What they found stunned the community. The gaseous halo extends approximately 1 million light-years from Andromeda's center. It is roughly 6 times larger and 1,000 times more massive than previous estimates had suggested. The halo contains approximately half as much mass as all the stars in the galaxy combined, distributed in a hot, diffuse shell that is completely invisible to optical telescopes. It is not a thin wisp at the galaxy's edge. It is an enormous envelope of material, tenuous by earthly standards but vast beyond reckoning, surrounding the visible galaxy on all sides and reaching outward into intergalactic space. 1 million light-years. The distance between Andromeda and the Milky Way is approximately 2.5 million light-years. That means Andromeda's gaseous halo reaches roughly 40% of the way to our galaxy. And if the Milky Way possesses a similar halo, which there is every reason to believe it does, the two halos are already touching, already overlapping, already mixing at the boundary between the two systems. Think about what that means. The gap you imagined between the galaxies, the clean black void separating one island of stars from another, does not exist. It was never empty in the way your intuition suggested. The space between us and Andromeda is occupied. It is filled with the outermost material of both systems, hot, diffuse gas that has been flowing outward from each galaxy for billions of years, gradually extending further and further into the intergalactic medium until the two envelopes met somewhere in the middle. No telescope has fully mapped the boundary. No instrument has precisely defined where Andromeda's halo ends and the Milky Way's begins. The transition is almost certainly gradual, a region where the density of gas belonging to one system slowly gives way to the density of gas belonging to the other, with no sharp edge, no clean line, no border. You are not separated from Andromeda by emptiness. You are separated from it by a gradient, a slow, continuous change in which systems material dominates the local space. And somewhere out there, roughly halfway between the two galaxies, in a region of intergalactic space that no human being will ever visit and no probe will ever reach, the atoms from Andromeda and the atoms from the Milky Way are drifting past each other in the dark. The two galaxies are already mingling. The interaction has already begun. It began long before anyone looked up and noticed the smudge. The more you look at Andromeda with instruments rather than eyes, the more it refuses to stay within the boundaries your intuition wants to give it. And the most recent observations have only intensified this effect. In early 2025, the Space Telescope Science Institute released the largest Hubble image of Andromeda ever assembled. The mosaic, compiled from over 600 individual snapshots taken across more than a decade, captured The glow of 200 million individually resolved stars spread across a section of the galaxy's disk spanning more than 40,000 light-years. 200 million stars, each one pinpointed as a separate source of light, and that was still only a fraction of the total population. The image required more than 2.5 billion pixels to contain. The purpose was not merely aesthetic. By resolving individual stars, astronomers can study their ages, compositions, and positions, reconstructing the history of how the galaxy was assembled over billions of years, including the mergers that left their signatures in the distribution and chemistry of the stellar population. That image was a reminder that even after more than a century of study, we are still cataloging the basic contents of Andromeda, still counting, still resolving, still discovering what is there. And in early 2026, that point was driven home again. A research team led by Joanna Sakowska at the Institute of Astrophysics of Andalusia announced the confirmation of Andromeda 36, a newly identified ultra-faint dwarf satellite galaxy orbiting within Andromeda's halo. The discovery was remarkable for several reasons. First, the galaxy was initially spotted not by an automated detection algorithm, but by an amateur astronomer, Giuseppe Donatiello, who was visually inspecting public survey images. A human eye caught what software had missed. Second, the object is extraordinarily faint. With a visual magnitude of approximately -6, it ranks among the dimmest galaxies ever detected. It is estimated to be roughly 12.5 billion years old, meaning it formed during the earliest epochs of galaxy assembly, and its extremely low metallicity, a measure of how few heavy elements its stars contain, suggests it has undergone almost no chemical evolution since its birth. It is a fossil, a relic from the infancy of the universe, quietly orbiting the giant that it somehow survived being consumed by. The discovery also reinforced a broader point. Andromeda may host close to 100 dwarf satellite galaxies, and roughly half of them remain undetected. Despite being the most studied external galaxy in the sky, Andromeda is still hiding significant components of its structure from us. Every new instrument, every deeper survey, reveals something that was previously invisible. The galaxy is not fully known. It is being uncovered, layer by layer, and every new layer makes it larger, more complex, and more consequential than the layer before. Take the globular clusters. Andromeda hosts approximately 450 of them, nearly 3 times the number found in the Milky Way. These ancient spherical swarms of stars, each containing tens of thousands to hundreds of thousands of members, are among the oldest objects in the galaxy. Some are as old as the universe itself. They orbit through Andromeda's halo in long elliptical paths that carry them far above and below the disk plane, carrying within their stellar populations a chemical record of the conditions under which they formed. Their orbital properties reveal that some were born in Andromeda and others were stolen from galaxies that Andromeda devoured. The globular cluster population is a graveyard record, a catalogue of the dead written in the movements of survivors. Put all of this together. A disk 220,000 light-years across, 1 trillion stars, a supermassive black hole weighing 100 million solar masses or more. A double nucleus whose offset bright spot is a gravitational illusion created by stars trapped on extreme orbits around that black hole. Spiral arms threaded with newborn stars and the gas that feeds them. A central bulge, scarred by past mergers. A stellar halo, bloated with the debris of at least 2 consumed galaxies. A dark matter halo extending more than 500,000 light-years outward and containing 90% of the total mass. A gaseous envelope reaching 1 million light-years toward us, already overlapping with our own galaxy's envelope in a region of intergalactic space that has no name and no border. Nearly 500 globular clusters, at least 36 known satellite galaxies, with potentially dozens more waiting to be found. And a 12.5 billion-year-old dwarf galaxy fossil still orbiting in its outskirts, so faint it was nearly lost forever. That is what the smudge is. That is what the poster on the wall is a picture of. And the photograph, the elegant spiral with its gentle arms and soft golden core, captures less of this reality than a postage stamp captures of the country it was mailed from. There is a particular kind of discomfort that comes from realizing an object you thought you understood is vastly larger and more complex than your mental model allowed. It is not fear in the ordinary sense. Nobody is going to be harmed by Andromeda's globular clusters. The supermassive black hole is not reaching across 2.5 million light-years to threaten anyone. The discomfort is subtler than that. It is the feeling of a mental frame breaking. The category you filed Andromeda under, beautiful, distant object, cannot hold what you now know about it. The frame is too small, and the part of your brain that builds and maintains your picture of the world does not like it when frames break, because broken frames mean the map was wrong, and a wrong map means the territory is less known than you thought. Andromeda is not a distant decoration. It is a colossal physical system, the largest gravitationally bound structure within roughly 3 million light-years of where you are sitting, assembled through billions of years of accretion, collision, and consumption, wrapped in an invisible dark matter shell that outweighs everything you can see by a factor of 9, breathing a gaseous halo that reaches toward our galaxy across the intergalactic void, and has already made contact with our own, and carrying at its center a gravitational engine that has been consuming matter since before our sun existed. And it is not sitting still. It is moving toward us. It has been moving toward us for billions of years. And the nature of that approach, what it means, what it might lead to, and what recent science has revealed about the uncertainty of the outcome, is where this story takes its sharpest turn. Because for decades, the scientific consensus was clear and simple. The Milky Way and Andromeda were destined to collide. The merger was treated as an inevitability, a fixed date on the cosmic calendar. It appeared in textbooks. It appeared in documentaries. It appeared in headlines that ranged from awed to panicked. Then, in 2025, a study published in one of the most respected journals in astrophysics rewrote that story entirely. And the new version is not more comforting, it is less. Because what replaced certainty was not safety. It was something the human mind handles even worse than a known threat. It was doubt. The measurement itself is simple, deceptively simple. When you point a spectrograph at the Andromeda galaxy and analyze the light arriving from its stars, the wavelengths are compressed, shifted toward the blue end of the spectrum. This is the Doppler effect applied to light. An object moving toward you compresses the waves it emits. An object moving away stretches them. Nearly every galaxy in the observable universe shows a redshift, meaning it is moving away from us as the universe expands. Andromeda does not. Andromeda is one of the very few galaxies anywhere in the sky that shows a blue shift. It is approaching, and it has been approaching for as long as anyone has known how to measure it. The approach velocity is approximately 110 kilometers per second relative to the Milky Way. That translates to roughly 250,000 miles per hour. The number sounds dramatic, and it is, but context matters here. At that speed, Andromeda closes the 2.5 million light-year gap by roughly 1 light-year every 3,000 years. In a human lifetime, the galaxy moves closer by an amount so small that no telescope in existence could detect the difference through direct imaging. The motion is real, but it operates on timescales that make geology look impulsive. This is one of the reasons the approach has been so easy to dismiss emotionally. A collision that might happen in 4 or 5 billion years feels like someone else's problem. It is filed alongside the eventual death of the Sun and the heat death of the universe in a mental category labeled things too far away to care about. But dismissing the approach because of its timescale is a mistake. Not because the collision is imminent, it is not, but because the timescale is the wrong thing to focus on. What matters is not when the interaction reaches its most dramatic phase. What matters is what the interaction tells us about the nature of the system we live in right now. The Milky Way and Andromeda are not two independent objects that happen to be drifting toward each other through otherwise empty space. They are the two dominant masses in a shared gravitational system. They have been influencing each other's trajectories since both galaxies formed. Every satellite galaxy in the local group, every dwarf spheroidal, every irregular cloud of stars scattered through the surrounding volume of space, exists in an orbit shaped by the combined gravitational field of these two giants. The approach is not an accident. It is the central dynamic of the largest structure within millions of light-years. For decades, the scientific consensus held that this dynamic had a single, inevitable conclusion. The galaxies would merge. The radial velocity was clear. Andromeda was heading toward us. The transverse velocity, the sideways component of its motion, was too small to carry it past us. Models run in the 2000s predicted a direct collision in approximately 4 to 5 billion years, followed by a chaotic gravitational dance lasting another 2 billion years, followed by the eventual formation of a giant elliptical galaxy that astronomers informally nicknamed Milkomeda. The story was neat. It had a beginning, a middle, and an end. It appeared in textbooks, in NASA press releases, in planetarium shows around the world. The Milky Way and Andromeda were doomed. The merger was written in the math. Then the math changed. In June of 2025, a study led by Til Sawala, published in Nature Astronomy, delivered one of the most significant revisions to this story in its history. The team used the most current and precise observational data available from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft to construct a new set of dynamical models of the local group's future. They ran over 100,000 simulations, and what they found upended the comfortable certainty that had persisted for more than a decade. The probability of a direct collision between the Milky Way and Andromeda within the next 5 billion years is approximately 2%. Not 50%, not 90%. 2. Extending the timeline to 10 billion years, the probability rises to roughly 50%. A coin toss, even odds. The galaxies might merge, they might not. The future of the two largest systems in the local group is not written in stone. It is balanced on a knife's edge of gravitational uncertainty. The team wrote it plainly. Proclamations of the impending demise of our galaxy appear to be greatly exaggerated. The reason for this dramatic revision comes down to something that previous models underestimated. The local group is not a two-body system. It is a multi-body system. And in multi-body gravitational problems, small differences in initial conditions can produce wildly different outcomes. 2 additional galaxies played the critical role in the updated simulations. The first is the Triangulum galaxy, also known as M33, the third largest member of the local group. Triangulum orbits in the general vicinity of Andromeda, and its gravitational influence tugs on the Andromeda Milky Way trajectory in a way that increases the likelihood of a merger. Including it in the simulations pushed the odds slightly upward. The second is the Large Magellanic Cloud, a satellite galaxy of the Milky Way that is far more massive than its modest appearance suggests. Recent measurements have revised its mass estimates sharply upward. The Large Magellanic Cloud's orbit runs roughly perpendicular to the line connecting the Milky Way and Andromeda. Its gravitational influence acts on our galaxy's trajectory in a direction that pulls us slightly off the collision course. Including it in the simulations pushed the odds downward, and the downward push turned out to be stronger than the upward push from Triangulum. The net result is that the fate of both galaxies depends on variables that are not yet measured with sufficient precision to produce a definitive answer. The transverse velocity of Andromeda, the exact mass of the Large Magellanic Cloud, the precise orbital parameters of Triangulum, the total mass of the dark matter halos surrounding each system, each of these carries uncertainties that, when propagated forward across billions of years, produce a spread of outcomes so wide that merger and non-merger are almost equally likely. This is not reassuring. The previous narrative, as dramatic as it sounded, had a strange comfort embedded within it. If the merger was inevitable, then at least the future was known. You could point to a moment on a timeline and say, that is when it happens. The uncertainty itself was contained. The new picture offers no such comfort. The future of our galaxy is genuinely unknown. The outcome depends on measurements that have not yet been made and forces whose exact magnitudes are still being debated. We live in a galaxy whose long-term fate is an open question, subject to gravitational influences that are currently being refined by spacecraft, measuring stellar positions to micro-arcsecond precision. The data from Gaia's upcoming releases may narrow the uncertainty, or they may reveal additional complications that widen it further. What the new study did not change is the fundamental nature of the interaction. Regardless of whether a full merger occurs within the next 10 billion years, the gravitational relationship between the two galaxies is permanent. They are bound. They are approaching. And the range of possible outcomes includes scenarios that are, in some ways, more structurally disorienting than a clean collision. In many of the simulations, the Milky Way and Andromeda do not merge on the first pass. They swing past each other at a distance large enough that their disks do not directly interact. But even in these flyby scenarios, the passage is not clean. Tidal forces during the close approach would stretch and deform both galaxies. Stars in the outer regions of each disk would be flung outward into long tidal tails that could extend hundreds of thousands of light-years into intergalactic space. The spiral structure of both galaxies would be disrupted. Satellite galaxies caught between the two systems would be scattered, some captured by the other galaxy, some flung out of the local group entirely. The gravitational reshaping would trigger waves of star formation as gas clouds are compressed and collapse. The night sky, if anyone were alive to see it, would be transformed beyond recognition. And after the first pass, if the galaxies did not escape each other's gravitational grip, they would slow, stop, and begin falling back toward each other for a second encounter, then a third. Each pass would strip more material from the outer regions. Each encounter would bleed orbital energy through a process called dynamical friction. Dynamical friction is one of those concepts that sounds technical, but describes something almost organic in its relentlessness. When two massive objects move through a shared field of dark matter and stars, the gravitational wake they leave behind acts as a drag. The dark matter particles and stars that each galaxy pulls toward itself during the encounter do not simply snap back to their original positions after the galaxies pass. They are displaced. They absorb energy from the orbital motion of the two galaxies and redistribute it as random internal motion within the halos. The result is that every close pass costs the system orbital energy. The galaxies slow down. Their orbits shrink. The next approach happens sooner than the last, and at a closer distance. And the one after that is closer still. There is no mechanism to reverse this process. Dynamical friction is a one-way valve. Energy flows from ordered orbital motion into disordered internal motion, and it does not flow back. Once two galaxies are close enough for dynamical friction to operate significantly, the outcome is not a question of whether they will merge, it is a question of how many orbits the process takes. 3 passes, 5, perhaps 10, spread across billions of years, but the direction is locked. The spiraling inward continues until the two systems occupy the same volume of space and their individual identities dissolve into a single, larger structure. This is what makes the 50% uncertainty from the 2025 study so structurally important. The question is not whether a merger would be dramatic. It would be. The question is whether the Milky Way and Andromeda will reach the distance threshold where dynamical friction becomes the dominant force. If they do, the merger becomes inevitable, regardless of what happens afterward. If they pass at a distance large enough to avoid significant frictional coupling, they may swing apart and maintain separate orbits for billions of additional years. The coin toss is not about whether the merger would be consequential. It is about whether the invisible ratchet of dynamical friction engages, and once it engages, it does not release. The end point of a full merger would be something fundamentally different from either galaxy that went into it. The ordered spiral structure of both the Milky Way and Andromeda would be destroyed. The combined system would relax into a giant elliptical galaxy, a massive, roughly spherical cloud of stars with no spiral arms, no defined disk, and no coherent rotation in the way spirals rotate. The stars that once traced elegant curves through Andromeda's arms and our own would be scattered into random orbits, filling a volume many times larger than either original galaxy. The gas and dust that fuel star formation in spiral galaxies would be largely consumed or heated during the merger, and the new elliptical galaxy would gradually go quiet, star formation would slow and eventually stop. The galaxy would age. The remaining stars would burn through their fuel over trillions of years, growing dimmer and redder until the light faded entirely. The two supermassive black holes, Andromeda's 100 million solar mass giant and the Milky Way's 4 million solar mass anchor, would follow their own trajectory through the merger. As the galaxies combined, the black holes would orbit each other at the center of the new system, gradually spiraling inward through dynamical friction as stars passing near them absorbed orbital energy and were flung outward. This process would take millions of years. As the distance between them shrank, they would begin to emit gravitational waves, ripples in the fabric of space-time itself, carrying energy outward and accelerating the inspiral. In the final moments, the two black holes would merge in an event so violent that the gravitational wave emission would briefly exceed the combined light output of every star in the observable universe. The resulting single black hole would settle into the center of the new galaxy and gradually go quiet, sitting in the dark for eternity. That is one possible future, a 50% chance, a coin landing on one side. On the other side of the coin, the galaxies pass each other and separate, continuing to orbit the common center of mass of the local group in long elliptical paths that may or may not bring them close again within the remaining lifetime of their stars. In this scenario, both galaxies survive as independent structures, scarred and deformed by the encounter, but not destroyed. The Milky Way would carry the marks of the interaction in its disrupted outer disk and scattered stellar populations for billions of years afterward. Either way, what the interaction makes clear is that our galaxy is not a self-contained system moving serenely through empty space. It is half of a gravitational partnership. It has always been half of a partnership, and the other half is a structure that is larger, more massive, invisible matter, carries a black hole 25 to 35 times heavier than ours, and has a documented history of consuming galaxies that were once the third largest systems in the neighborhood. Now, there is a detail about the collision scenario, or the flyby scenario, or any scenario involving the close approach of these two galaxies that often gets buried beneath the spectacle of the larger narrative. And it is worth pausing on, because it is the detail that most directly connects this cosmic scale event to the human scale question of what it means. During a galactic merger, the stars almost never collide. The distances between stars within a galaxy are so vast relative to the sizes of the stars themselves that two galaxies can pass through each other and not a single stellar collision occurs. This is counterintuitive. The word collision suggests impact, destruction, contact, but galactic collisions are not collisions in the way a car crash is a collision. They are gravitational interactions. The damage is done not by contact but by tidal forces, the differential pull of gravity across extended objects, which can tear structures apart without any two solid bodies ever touching. This means that, if you were living on a planet orbiting a star in the Milky Way during a close encounter with Andromeda, the experience would not be a sudden catastrophe. It would be the slowest, most immense transformation any living thing could witness. Over millions of years, the faint smudge you once saw in the constellation of Andromeda would grow. Year by year, century by century, it would expand across the sky as the distance between the galaxies shrank. What started as a barely visible glow would gradually resolve into structure. You would begin to see the spiral arms, not as details in a photograph, but as rivers of light stretching across your actual sky. The bright central bulge would swell into a luminous core, visible even in daylight, rivaling and eventually exceeding the brightness of the Milky Way's own band of stars. The sky that had been dominated by a single galaxy's worth of stars would begin to fill with a second galaxy's worth, overlapping, interleaving, creating a canopy of light denser and more complex than anything that exists tonight. And then, the tidal forces would begin to express themselves visibly. The spiral arms of the Milky Way, the very structure you live inside, would start to distort. Stars at the outer edges of the disk, the ones most loosely bound to the galactic center, would be tugged outward toward Andromeda in long tidal streamers that would arc across the sky in luminous bridges between the two systems. New star formation, triggered by the compression of gas clouds as the galaxies interacted, would ignite vast nebulae across both systems simultaneously, filling the sky with glowing regions of ionized hydrogen in shades of red and pink that stretched from horizon to horizon. The familiar constellations would dissolve, not because the stars had moved in any way you could perceive in a single lifetime, but because across the timescale of the interaction, millions of years, the entire stellar backdrop would be rearranged by forces operating on a galactic scale. The night sky, during a close encounter, would not be dark. It would be blazing. 2 trillion stars, the combined population of both galaxies, visible simultaneously from a planet embedded in the middle of the interaction. The sky would be so full of light that the concept of a dark background punctuated by points of brightness would no longer apply. The background itself would glow. And yet, through all of this, the odds of your specific star being struck by another star, or your specific planet being gravitationally disrupted to the point of ejection from its orbit, would be extraordinarily small. The distances between stars, even within the densest regions of the merging galaxies, are measured in light years. The stars themselves are measured in light seconds. The ratio of empty space to occupied space within a galaxy is so overwhelmingly lopsided that 2 galaxies can pass through each other the way 2 swarms of gnats can pass through each other, with almost no physical contact between individual members. You would not be hit. You would be rearranged. That distinction matters because it corrects a common misconception while introducing a more subtle form of unease. The danger of Andromeda is not that it will destroy our planet. The danger, if you can call it that, is structural. It is the realization that the Milky Way is not permanent. It is not a fixed stage on which the story of life plays out. It is a temporary configuration of matter held in a shape that depends on conditions that are actively changing. The spiral arms will not last. The disk may not last. The galactic address we take for granted, our position in a specific arm of a specific galaxy with a specific structure, is contingent on forces that are larger than the galaxy itself. And those forces are not limited to Andromeda. The local group, the collection of more than 80 galaxies bound together by gravity, is itself embedded in a larger structure. The local group sits at the outskirts of the Virgo supercluster, a vast congregation of galaxy groups and clusters spanning roughly 110 million light-years. The Virgo supercluster, in turn, is part of an even larger structure called the Laniakea supercluster, a basin of gravitational attraction containing roughly 100,000 galaxies spread across 500 million light-years. The name Laniakea comes from Hawaiian and means immeasurable heaven. Within Laniakea, galaxies are not static, they are flowing, pulled by gravitational gradients toward regions of higher density, the way water flows downhill toward the lowest point in a landscape. The local group is moving toward the center of the Virgo cluster. The Virgo cluster itself is moving toward a region called the Great Attractor, an enormous concentration of mass, located roughly 150 million light-years away, in the direction of the Centaurus and Norma constellations. The Great Attractor deserves more than a passing mention, because it embodies the same principle that makes Andromeda unsettling, scaled up to a level that is almost incomprehensible. It is one of the most massive concentrations of matter in the observable universe within our cosmic neighborhood. Its gravitational influence is pulling hundreds of galaxies toward it at velocities of several hundred kilometers per second. The flow is real. It is measured. It is confirmed by multiple independent observations of galaxy-peculiar velocities across the region. And yet, the Great Attractor itself is largely hidden from direct observation. It sits behind the zone of avoidance, the thick band of dust and stars along the plane of our own galaxy that blocks visible light from passing through. We know it is there because of its gravitational effects. We can map its approximate position and estimate its mass, but we cannot see it clearly. The structure that governs the trajectory of our entire supercluster is obscured by the galaxy we live in. That fact should echo through everything you have heard in this story. Andromeda looks like a calm smudge because your eyes cannot detect its true extent. Its dark matter halo is invisible because dark matter does not interact with light. Its gaseous envelope is invisible to optical telescopes. And now, even the largest gravitational structure influencing our cosmic trajectory is hidden behind the plane of our own disk. At every scale, the forces that shape where we are going are the forces we cannot see. The universe does not hide its most important structures because they are far away. It hides them because the instruments we evolved to use, our eyes, our intuitions, our perceptual habits, were never built to detect them. The visible universe is the thin, bright surface. The real universe is the dark architecture underneath. And the deeper you look, the more of that architecture turns out to be invisible. This layered motion means that the Milky Way is not simply approaching Andromeda. It is simultaneously being pulled toward the Virgo cluster, toward the Great Attractor, and toward the center of Laniakea, while also participating in the overall expansion of the universe that carries the entire Laniakea supercluster away from other superclusters at ever-increasing speed. The comfortable picture of a galaxy sitting calmly in space is an illusion at every scale. At the scale of the local group, we are in a gravitational dance with Andromeda. At the scale of the supercluster, We are falling toward concentrations of mass we cannot fully see. At the scale of the observable universe, we are being carried outward by an expansion we cannot stop. Nothing about our position in space is static. Nothing about it is settled. Andromeda is the most visible reminder of this fact. It is the one object in the sky that a human being can see with bare eyes and say, truthfully, that is another galaxy, and it is gravitationally interacting with the one I am standing in right now. Every other galaxy visible without a telescope is either a satellite of the Milky Way, like the Large and Small Magellanic Clouds, or too faint to be seen from most locations. Andromeda is unique. It is the one window that the naked human eye has into the reality of intergalactic structure. And what it shows, if you understand what you are looking at, is not calm. It is motion. It is interaction. It is a gravitational relationship whose outcome is literally uncertain. The 2025 study carried another implication that has received less public attention, but may be more significant in the long run. The simulations did not simply calculate whether the galaxies would merge. They mapped the range of possible trajectories for the entire local group over 10 billion years. In some scenarios, the merger between the Milky Way and Andromeda triggers a cascade of interactions among the satellite galaxies that fundamentally restructures the local group. Dwarf galaxies are flung out of the group entirely. Others are captured by the merged remnant and consumed. The Triangulum galaxy, in some simulations, is pulled into the merger and destroyed. In other simulations, it survives as an independent system but on a radically different orbit. The local group, in other words, is not a stable neighborhood. It is a set of gravitational relationships that are sensitive to initial conditions and capable of producing dramatically different configurations depending on how a few key variables evolve. The neighborhood you live in is contingent. It could look completely different in a few billion years, and the primary driver of that change is the relationship between the two galaxies you are already familiar with. There is one more dimension to the approach that deserves attention, because it connects the physics to something that operates on a timescale the human mind can actually engage with. Andromeda is approaching at 110 kilometers per second. That is more than 14 times the speed at which the International Space Station orbits Earth. In the time it took you to hear the last 3 sentences, Andromeda moved approximately 500 kilometers closer. In the time since you started listening tonight, the gap has closed by several thousand kilometers. By tomorrow morning, it will have closed by roughly another 10 million kilometers. By the end of this year, the reduction will be approximately 3.5 billion kilometers, a distance greater than the gap between the Sun and Uranus. None of this changes your daily life. None of it registers on any instrument you will ever hold. But it is happening, continuously, while you eat breakfast, while you sleep, while you worry about things that feel urgent and close. The largest gravitational interaction within millions of light years is ticking forward in the background at a pace that never pauses and never slows. The ancient Persian astronomer who first recorded Andromeda as a faint cloud in the sky saw a galaxy that was measurably farther away than the one you see tonight. Every human being who has ever lived and looked at Andromeda saw it at a slightly different distance. The galaxy was farther from the Neanderthals, who may have gazed upward at it without knowing what it was. It was farther from the Babylonians, who mapped the constellations around it. It was farther from Hubble, when he first resolved its stars. Each generation inherited a sky in which Andromeda was incrementally closer than the generation before. And every generation that comes after you, if there are generations that come after you, will inherit it closer still. The approach does not stop. The gravitational relationship does not pause. And the uncertainty about what happens at the end of that approach, whether the galaxies collide or swing past each other or spiral together across multiple encounters over billions of years, is not an uncertainty that will be resolved by waiting. It will be resolved by gravity, operating on dark matter halos we cannot see, along trajectories shaped by satellite galaxies whose masses we are still measuring, across timescales that reduce the entire history of human civilization to a rounding error. That is the reality of living next to Andromeda. Not a threat, not a countdown. A relationship whose terms are dictated by physics operating on scales that human beings were never equipped to perceive, let alone control. The approach is measured, the outcome is not. And that combination, certainty of process married to uncertainty of result, is the signature of a system that does not care whether its inhabitants find the arrangement comfortable. Andromeda does not care. It is not malicious. It is not aiming at us. It is a trillion stars, bound in a dark matter shell, following a trajectory set by the distribution of mass in the early universe. Approaching a system of 200 to 400 billion stars bound in their own dark matter shell, with the outcome depending on variables that were determined before either galaxy existed in its current form. And the reason that matters, the reason any of this should unsettle a person sitting safely on a planet where the next sunrise is guaranteed, is not about the collision. It is about what the collision question reveals. It reveals that the galaxy you call home is not the stable, permanent, self-contained system that your intuition insists it is. It is a participant, a member of a gravitational community. A body in motion, being acted upon by forces that originate in objects you can barely see and structures you cannot see at all. That is the deeper discomfort. Not that Andromeda might hit us. That Andromeda exists at all in the way that it does, as a real, massive, approaching neighbor whose gravitational influence is shaping the trajectory of your galaxy right now, tonight, while you sit here thinking it through. And that discomfort has one more layer, one that moves beyond the physics of orbits and halos and dark matter, and into the question that the entire story has been building toward. Not what Andromeda will do, but what Andromeda means. What it tells us about the kind of universe we are living in, and why the most beautiful object you can see in the night sky might also be the most honest one. There is a way of looking at the night sky that almost every human being defaults to without being taught. You go outside, you look up, you see points of light scattered across a dark background, and your brain, without any conscious effort, turns that into a ceiling, a dome, a fixed surface at some vaguely defined distance above you, decorated with glowing objects that feel more or less the same distance away. Stars and planets and the faint wash of the Milky Way and the occasional smudge of something dimmer all get compressed into a single flat layer. A sky, a backdrop, a stage set behind which nothing further exists. This is not a failure of intelligence. It is a feature of neurology. The human visual system evolved to assess threats and opportunities on a savanna, not to pass the three-dimensional structure of a universe that extends for billions of light years in every direction. Your eyes have no mechanism for sensing depth at cosmic distances. There is no parallax, no atmospheric perspective, no relative motion fast enough to trigger stereo vision. Everything farther than a few thousand miles collapses into a single plane. And so, the brain does what it always does when it lacks data. It fills in the gap with something manageable. A dome, a ceiling, a flat and finite sky. Andromeda breaks that ceiling. Not violently, not suddenly, but with a patient, structural insistence that, once you understand it, cannot be unfelt. When you see Andromeda with your bare eyes, you are not looking at a point of light. You are looking through the depth of the universe. The photons hitting your retina have been traveling for 2.5 million years. They left their source before your species existed. They crossed intergalactic space a void so empty that the average density of matter within it is roughly 1 atom per cubic meter. They passed through the Milky Way's own halo of gas and dark matter. They entered our galaxy's disk. They passed through the interstellar medium between the stars of the Milky Way. They entered our solar system. They passed through Earth's atmosphere. And they landed on a cluster of cells at the back of your eye that evolved to detect ripe fruit and approaching predators. The mismatch between the instrument and the signal is staggering. Your eye is receiving information from a structure containing 1 trillion stars, embedded in a dark matter halo spanning hundreds of thousands of light years, surrounded by a gaseous envelope reaching 1 million light years outward, approaching at 110 kilometers per second, carrying at its center a black hole 100 million times the mass of the Sun. And your brain turns all of that into a faint smudge and files it under background. That filing is the comfortable sky. And everything in this story has been working to collapse it. The comfortable sky is the version of the universe that human intuition constructs by default. It is the version where stars are decorations, galaxies are distant abstractions, and the space between them is a harmless void. It is the version where Earth sits at the center of something manageable, surrounded by a dome of lights that exist primarily to be beautiful. The comfortable sky is not a belief system. It is not a deliberate error. It is a perceptual habit so deeply wired that most people live their entire lives inside it without noticing. And it is wrong. Andromeda is the most accessible proof that it is wrong. Not because Andromeda is the strangest or most extreme object in the cosmos. It is not. There are quasars billions of light years away that outshine entire galaxies. There are neutron stars that spin hundreds of times per second. There are black holes in distant galaxy clusters with masses measured in the tens of billions of solar masses. Any one of these is more extreme than Andromeda in isolation, but none of them can be seen with the naked eye. None of them sits close enough to share a gravitational system with our galaxy. None of them forces the confrontation that Andromeda forces, which is the confrontation between what the sky looks like and what the sky actually is. A quasar is terrifying in the abstract. Andromeda is terrifying in the specific because it is right there. You can walk outside tonight and see it, and the gap between what you see and what it is measures the gap between the comfortable sky and the real one. Let us trace what filling that gap actually requires your mind to do, because the collapse of the comfortable sky is not a single realization. It is a sequence of them, each one removing a layer of insulation between the human sense of place and the raw structure of the cosmos. The first layer to go is isolation. In the comfortable sky, the Milky Way is alone. It sits in its own private darkness, separated from everything else by distances so vast they might as well be infinite. The stars you see are all local. The space between galaxies is someone else's problem. Andromeda destroys this layer. The Milky Way is not alone. It shares a gravitational system with another galaxy that contains more stars, a more massive black hole, a larger disk, and a longer history of consuming its neighbors. The two systems are connected by real physical forces operating right now, at this moment, at every moment. The isolation was never real. It was an artifact of limited perception. The second layer to go is stability. In the comfortable sky, the galaxy is a permanent structure. It has always been a spiral. It will always be a spiral. The Sun orbits within it, the way a car orbits a racetrack, endlessly, predictably, within a system whose layout is fixed. Andromeda destroys this layer too. The Milky Way's spiral structure is not permanent. It is a configuration maintained by a balance of forces that are subject to disruption. The gravitational interaction with Andromeda, whether it leads to a merger or a flyby, will alter the galaxy's structure on timescales that are long by human standards but short by cosmic ones. The spiral arms may unwind, the disk may warp, stars may be flung into intergalactic space. The shape of the galaxy you live in is not a given. It is a snapshot of a structure in the middle of a process. The third layer to go is centrality. In the comfortable sky, there is a quiet hierarchy. Earth is the ground, the solar system is the neighborhood, the Milky Way is the city, and everything else is far away, disconnected, irrelevant to daily existence. Andromeda reveals that this hierarchy is a comforting fiction. The local group is the actual neighborhood, and within it, the Milky Way is not the dominant player in every respect. Andromeda is larger in visible extent. It contains more stars. Its black hole is more massive. Its history of mergers is more violent. The Milky Way is not the center of its own context. It is one of two major members in a system where the other member is, by several measures, the more imposing one. The psychological comfort of feeling like you live in the biggest, most important galaxy in the area does not survive contact with the data. The fourth layer to go is emptiness. In the comfortable sky, the space between galaxies is a void, a gap, nothingness separating one island of matter from the next. The discovery of Andromeda's gaseous halo, extending 1,000,000 light-years outward, reaching nearly halfway to the Milky Way, erases this. If both galaxies possess similar halos, and there is no physical reason to think they would not, then the two systems are already in contact, not through stars, not through visible matter, but through vast envelopes of hot, diffuse gas that overlap in the intergalactic medium. The gap between the galaxies is not empty. It is a transition zone, a region where the outermost breath of one system mingles with the outermost breath of the other. You are not separated from Andromeda by a void. You are separated from Andromeda by a gradient. The fifth layer to go is predictability. In the comfortable sky, the future is known. The sun will rise. The seasons will cycle. The stars will hold their positions. The galaxy will continue as it is. The 2025 study demolished this layer with surgical precision. The future of the Milky Way depends on a gravitational calculation whose key variables are not yet known with sufficient accuracy to determine the outcome. A 50% probability of merger. A 50% probability of survival as a separate system. The future of your galaxy is a coin toss, and the coin has not yet landed, and it will not land for billions of years. The comfortable sky promised that the large-scale structure of your cosmic environment was settled. It is not. It is an open question, balanced on measurements that have not yet been made. Strip away these 5 layers, and what remains is the real sky. The one that Andromeda has been trying to show you every time you glanced up and saw a faint smudge and felt nothing but calm. The real sky is not calm. The real sky is a dynamic, interconnected, gravitationally active space in which the galaxy you inhabit is locked into a relationship with a neighboring system of extraordinary scale, violent history, and uncertain future. The real sky contains no isolation, no permanent structure, no guaranteed stability. It contains motion, interaction, contingency, and consequence operating across timescales that dwarf human comprehension. And the real sky does something that the comfortable sky never did. It places you inside the structure rather than outside it. In the comfortable sky, you are an observer. You look up at the cosmos the way you look at a painting in a museum. The painting exists on a wall. You exist in front of it. There is a boundary between you and it. In the real sky, there is no wall. There is no frame. You are not looking at the universe. You are embedded in it. The galaxy you live in is being pulled by the galaxy you are looking at. The gas surrounding your galaxy is mixing with the gas surrounding that galaxy. The dark matter halo that holds your solar system in its orbit extends outward toward the same dark matter halo that holds 1 trillion stars in Andromeda's disk. You are part of the structure you are observing. The observer and the observed are gravitationally entangled. This is the collapse. Not a physical collapse, a conceptual one. The moment when the distance between you and Andromeda stops feeling like a buffer and starts feeling like a connection. The moment when the smudge stops being a decoration and starts being a neighbor. The moment when the sky stops being a ceiling and starts being a medium through which forces are transmitted, influences are exchanged, and futures are determined. There is a reason this collapse is uncomfortable, and it is worth naming precisely, because vague language fails here. The discomfort is not about danger. Andromeda is not going to hurt anyone hearing this. The approach is real, but the timescale is measured in billions of years. The merger, if it happens, will not involve stellar collisions. No planet will be struck. No civilization will be crushed by an incoming galaxy. The discomfort is not about death or destruction in any direct sense. The discomfort is about scale. Specifically, about the mismatch between the scale at which human life operates and the scale at which the universe is structured. Human beings experience reality in a band roughly bounded by the microscopic on one end and the planetary on the other. Within that band, intuition works. You can judge distances, estimate speeds, assess threats, and navigate your environment using the perceptual tools evolution gave you. Outside that band, intuition fails. And Andromeda sits so far outside that band that encountering it honestly requires accepting that the tools you use to understand the world simply do not function at this level. You cannot feel the approach of a galaxy. You cannot perceive the gravitational interaction between two dark matter halos. You cannot sense the mixing of circumgalactic gas in the intergalactic medium. You cannot watch a spiral arm unwind over 300 million years. You cannot experience the tidal deformation of a galactic disk during a close encounter. Every single one of these things is real, confirmed, measured by instruments of extraordinary precision, and every single one of them is completely invisible to the set of senses you were born with. Andromeda does not terrify the way a predator terrifies, by triggering an immediate survival response. It terrifies the way a revelation terrifies, by showing you that the framework you were using to understand your situation was missing most of the picture. The predator tells you that you are in danger. Andromeda tells you that the concept of safety you were relying on was built on incomplete information. The first is a threat, the second is a correction. And corrections, when they are large enough, can be more destabilizing than threats. Think about what the comfortable sky offered. It offered a universe where galaxies were distant, separate, static objects that existed primarily as photographic subjects. Where the Milky Way was a self-contained permanent home. Where the space between things was empty and inert. Where the future of the cosmic environment was settled and irrelevant to anything that mattered on human timescales, that picture felt safe. Not because it was accurate, but because it allowed you to believe that the largest structures in the universe operated in a domain completely separate from your own. Andromeda collapses that separation. It says, no, you are inside the structure. The structure is active. The structure is changing. The structure contains forces and interactions and uncertainties that operate on scales you cannot perceive, but that shape the context in which everything you care about exists. Your galaxy is not a closed room. It is an open system, connected to its neighbors by gravity and gas and dark matter, engaged in a relationship whose outcome is not known. Embedded in a larger flow of matter toward concentrations of mass that have not been fully mapped, the comfortable sky was a simplification. The real sky is a system. And you are a component of that system, whether you registered the fact or not. This is what it means to say Andromeda is more terrifying than it looks. It does not mean Andromeda is secretly ugly or secretly dangerous in some immediate, actionable sense. It means that the most beautiful object in the night sky, the one you can see with your own eyes, the one that generations of photographers have captured in images of stunning elegance, is also the single most potent corrective to the illusion that the universe is a safe, static, distant backdrop to human life. Every time a person looks at Andromeda and feels calm, the calm is real, but the basis for it is not. The calm comes from the compression, the flattening, the reduction of a colossal neighboring galaxy into a faint smear that fits comfortably inside the perceptual framework of a species that evolved to track motion on a savanna. The reality behind that smear is a structure of 1 trillion stars, 100 million solar mass black hole, a dark matter halo containing 90% of the total mass, a gaseous envelope already reaching toward us across the intergalactic medium, a documented history of galactic cannibalism, a confirmed gravitational approach, and a future that the best simulations in the world can only resolve to a coin toss. And you can see it with your bare eyes. Tonight. If the sky is clear and the city lights are low and you know where to look, you can stand on the surface of a small rocky planet orbiting an ordinary star in the outer disk of a mid-sized spiral galaxy. And you can look northeast past the great square of Pegasus, and you can see, with the same retina that evolved to find berries and avoid snakes, the light from a neighboring galaxy that has been traveling toward you for 2.5 million years. And you can feel calm, and you can know that the calm is the lie. Not because the universe is hostile. It is not hostile. Hostility requires intent, and the cosmos has none. Not because Andromeda is evil or malicious or aimed at you. It is none of those things. But because the calm depends on not knowing what you are looking at, and now you know. You know the smudge is a colossus. You know the distance is a connection. You know the beauty is a surface stretched over a depth that your nervous system was never designed to register. The most terrifying thing about Andromeda is not its size, though its size is beyond ordinary comprehension. It is not its black hole, though its black hole outweighs our own by a factor of 30. It is not the approach, though the approach is real and continuous. It is not the merger, though the merger remains a genuine possibility balanced on uncertain variables. The most terrifying thing about Andromeda is that it is the clearest reminder available to the human eye that the universe was never built for comfort. The galaxy you live in is not a sanctuary. It is a structure, temporary in its current form, embedded in a web of gravitational relationships, subject to forces that were set in motion before the Earth existed and that will continue operating long after the Earth is gone. And the object that tells you this, the messenger that carries this information from the real sky to the comfortable one, is not hidden. It is not locked behind a telescope or buried in a dataset or confined to the pages of a journal that only specialists read. It is right there, visible to the bare eye, waiting to be seen for what it is by anyone willing to look past the beauty and into the depth. The faint glow you see in the constellation of Andromeda is 2.5 million years old. It left a galaxy of 1 trillion stars when the most advanced creature on Earth was chipping stones in an African valley. It crossed a void that is not truly a void. It arrived at a planet that orbits a star, that orbits a galaxy, that is gravitationally bound to the very object that sent the light. And when it reached your eye, your brain did what it was built to do. It made the signal small. It made the source distant. It made the sky feel safe. But the sky is not safe. The sky is not a ceiling. The sky is not a backdrop. The sky is a window into a universe where galaxies interact, structures evolve. Dark matter shapes the fate of everything visible. And the two largest systems in your cosmic neighborhood are locked in a gravitational relationship whose resolution will determine the shape of everything within millions of light years for billions of years to come. Andromeda is not more terrifying than it looks because it hides some secret weapon or conceals an imminent threat. It is more terrifying than it looks because it looks like nothing, and it is everything. It is the nearest, clearest, most visible proof that the universe operates at scales and speeds and degrees of complexity that the human mind can understand intellectually but cannot feel intuitively. And the gap between understanding and feeling is the gap in which the comfortable sky survives. Tonight, if the weather allows, you can step outside and close that gap by a fraction. You can find the constellation. You can locate the smudge. You can look at it and hold in your mind, even for a few seconds, the knowledge of what it actually is. A galaxy, a neighbor, a colossus, a system of 1 trillion stars and 100 million solar mass black hole, wrapped in dark matter and breathing gas across the void toward the galaxy you are standing in. You will still feel calm, the smudge will still look faint, your brain will still try to file it under harmless, but somewhere beneath the calm, if you let the knowledge settle, there will be a new weight, a quiet awareness that the sky is deeper than it appears, and that one of the most beautiful things in it is also one of the most honest. Because Andromeda does not lie about what the universe is. It only looks like it does. The lie is in the eye. The truth is in the light. And the light has been traveling toward you for 2.5 million years, carrying a message that does not require translation. You are not alone in the dark. And the thing beside you is larger than you ever imagined.